today I'm going to present the HelpSteer series, an exploration into RLHF data curation. I'm Zilin, and I'm a senior applied scientist at NVIDIA. Below is my my personal website. Feel free to go there. You can find ways to contact me. Okay, so the first question is, the motivation for collecting RLHF dataset. And so to put that into broader perspective, I want to kind of introduce how humans collaborate with automated tools to curate training data for general domain LLMs in general. Okay, so the first related field is internet search, and the second related field is NLP tasks such as question answering and summarization. So in the era of internet search, researchers typically identify some features they believe is important for search relevance. For example, page rank proxies for page popularity, while text overlap with search term proxies for relevance. And then, we have prompts, which are basically search queries, as well as documents from internet users. These are basically websites as ways to match things. And we use some algorithms to find values for each feature, sometimes with the help of internet users. So for example, Google will have this, A/B test for whether, a particular search feature or particular variant of the PageRank algorithm will actually improve user experience. The next set of related task is NLP task. And this refers to traditional NLP tasks, including but not limited to question answering summarization, where, for example, for question answering, it consists of having a document and also having mostly like a one-liner question with extracted short span answer from this document. While for summarization, we basically take a document snippet and convert it into a short paragraph that condenses the meaning. And most of the time, this document are typically from internet users, such as Wikipedia, and crowd workers answer tasks and sometimes provide prompts. For example, in Squad, crowd workers also come up with the prompt instead of just, being given the prompt. Okay, so I also want to give a quick introduction to what RLHF is for people who might be less familiar. So this part where, is typically the first step, which is SFT. This is strictly speaking not part of RLHF, where you just train a model to resemble how humans perform a task. So this is also known as, behavioral cloning, depending on, the people you work with. The second stage of this is actually reward modeling, where basically given two responses to the same prompt, humans can select which one is better, and you train a model to kind of just predict which one is better. And finally, you can use a policy, either PPO or more recently GRPO or some of the other algorithms to optimize the model such that it maximizes the reward from the reward model earlier. Okay, so to kind of set a better scene for what we did in collecting our own RLHF data, I would also like to highlight how other people have collected their preference data. So I guess the first and perhaps, at that time, the most popular data set is actually Anthropic's HHRHF. And in this setting, the researchers decided on the annotation format. So they decided that, it's important to have preference ranking. And they then had prompts from crowd workers, while, the responses are sampled from LLMs. And finally, preference ranking are from crowd workers. The next kind of very common dataset is called Open Assistant. And it's kind of similar, but here it's more of like a crowdsourced effort where, most people are volunteers. And the researchers within this team decide the annotation format, in which case they choose both Likert ranking and preference. And we have prompts from volunteers. But this time around, differently from Anthropic's HHRHF, the responses are also from other volunteer crowd workers. And finally, the response annotations are also from volunteer crowd workers. So basically, humans try to pretend to be every part of the process. So why did HHRHF and Open Assistant differ? So HHRHF's main purpose is to improve anthropic models, whereas Open Assistant seeks to replicate ChatGPT with volunteers. They also have a difference in resources. Anthropic has access to LM that they can comfortably chat with, whereas when Open Assistant first started in January 2023, there wasn't really a chat model API available. ChatGPT, had just taken place back in November 2022, and they have yet to launch a public-facing API. Okay, so this brings me to the first part of my talk, which is the original HelpSteer, which we've finished in November 2023, and we presented this at NACO. So, as I mentioned previously, for example, Open Assistant and Anthropic HLHF, they're really good and they're also permissively licensed. But in terms of like raw performance in aligning models, they don't seem to be that good. At the same time, in the community, there are other datasets such as Ultra Feedback and Nectar. And these datasets are more generated entirely by GPT-4. And, the models that people have been able to use to create them, have been really, really good. And but the problem is, because it's distilling from GPT-4, there's a lot of legal implications with using them outside of academic or non-commercial settings. And at NVIDIA, we try to help everyone to align models. So we're acutely aware of this potential risk. And so we wanted to build something that is both good for aligning models and also fully open source. So because of that, we kind of annotated our own dataset, and this dataset is called HelpSteer. So this consists of 37 LM responses, each with a Likert 5 scale ranking on 5 attributes. So helpfulness, correctness, coherence, complexity, and verbosity. We trained what was at that time one of the best open source models, Llama 2 70B with HelpSteer and SteerRM method. And this helped us to achieve 7.54 MT bench, which is the highest amongst models not requiring data from GPT-4 at that time. We then fully open sourced this dataset on Hugging Face. So the question from some of you might be, why do you want to collect multiple attributes instead of just binary preferences? And at that time, I guess our initial effort was kind of like we tried HLHF and we also tried Open Assistant. And we found that if we just work with preferences, there's a lot of like learning of unexpected features. For example, I think one of the most important thing that we learned back then was that if you just model on this kind of preferences, the length actually influences user kind of like preferences quite a lot. And at that time, longer responses actually, are much more preferred by people generally. And if you just train models with that kind of like preference, the model actually doesn't know, how to separate longer responses from actually helpful responses. And so we thought, rather than modeling them together, let's model them separately so that, users can kind of determine how long the responses they actually want and whether they will penalize or reward longer responses. We also found that, with this kind of multiple attributes, we were able to train models more efficiently. So with HelpSteer, we only used the 7,000 samples versus with HLHF, we actually had to use, the entire 320K responses. So we collected this dataset by first curating 10,000 singleton prompts from diverse tasks. So we first got this task distribution from the InstructGPT paper, where I think they have about 10 tasks that they were mostly interested in. And we generated 4 model responses per prompt using an in-house 43 billion model. We then engaged human experts to annotate each response on a Likert 5 attribute. And I guess the important part of this is that not only do we have humans annotate this, but we also had people, it's the second layer of people looking through this to make sure that the annotations were indeed correct. And after we filtered out some of the less satisfactory responses, we have 37,000 high quality annotated prompt response pairs. So compared to the existing datasets like Open Assistant, our prompts were substantially longer because we have tasks involving context documents such as summarization, where you need to have a page or multiple pages of documents for them to then summarize. We also found that responses were generally very coherent. moderate on correctness, but low on complexity and verbosity. And finally, we found that in terms of overall helpfulness of the response, we find that answer correctness, I need to say, whether they're actually correct based on real world knowledge, and cohere actually, and logically coherent, strongly correlate with them. The next thing we did was to measure some of these aspects. So we have 5 different attributes, and we devised a measurement metric for each of them. There is empty bench, which at the time was very popular, and also truthful QA for correctness. And we found that basically compared to some of the other methods that we used, and also the baseline Llama 2 chat model, or kind of like RLHF with HTTP-RLHF, or DPO with Open Assistant, or DPO with HTTP-RLHF, we found that our method was able to outperform across nearly all metrics. And I guess the most important one is empty bench, as well as truthful QA. We then also conducted a short human evaluation, and we found that our model was able to kind of like have rather good win rates against both Llama 2 chat as well as RLHF with HTTP-RLHF model. Okay, so we also did an ablation to figure out what exactly was very important, and we basically removed one attribute at a time, and we find that response correctness is super important, right? So if you just remove kind of like correctness, it actually leads to a very big drop in performance. And we also found that HelpSteer was more important than Open Assistant, and in either case where we have some form of like likely attributes, is actually better than just doing SFT by itself. In this method, we are also able to give Likert scores to different models, different model attributes and inference time. So we could steer the model to generate more or less complex or more or less verbose response at inference time. And we thought that it's super useful for people to be able to give different complexity, because it's useful for personalization, education, and also for business settings. Okay, so moving on, this is now HelpSteer2, and this is a good 7 months after we released our first model, and we presented this at NeurIPS just earlier last year. And so similar problem. So at that time, we have both proprietary models and open weight models, including Qwen, that do not release alignment data. And we find that the same alignment data sets that were released at that time, they're also not commercially friendly, and same problem. And we wanted to kind of see if we can build a data set that is stronger than some of the existing commercial friendly data sets, but also with a commercial license. Okay, so at this time, we built this HelpSteer2, and interestingly, when we used to train a 340B model, this model achieved the best empty bench, the best reward bench at that time. And afterwards, all top 10 models on reward bench, which is open benchmark for reward models, also started using it. And compared to the previous kind of our first iteration, this actually reduced in size to only becoming 10K parent size. And so this kind of let us know that actually, if you have really high quality data, maybe the absolute quantity of data doesn't really matter. We also similarly released this on Hugging Face, again with the same license, and it accumulated more than 30,000 downloads in 4 months. So compared to HelpSteer1's data collection effort, we implemented a few changes. So the first being, rather than just sticking to one model, we actually use a range of stronger and more diverse models. So this includes our Nemotron 2 series, our Nemotron 3 series, and our Nemotron 4 series, as well as the external Mixtro 8x7B, which at that time was super strong. We also use multi-turn prompts. So in HelpSteer1, it was just singleton, like a prompt and response. So this time around, part of our dataset was actually also multi-turn prompts, where we have previous conversations, and we wanted to model these rewards in the context of not only the first user request, but also maybe a follow-up user request, where there is a previous assistant turn and a previous user turn. We also found that it was useful to have multiple annotators per task. So in HelpSteer1, we only had one annotator per task. And HelpSteer2, we actually increased that to 3 to 5 annotators per task. So whether it's 3 to 5 really depends on how much the initial 3 annotators disagree. So if they all agree, we could stop there. But if they disagree a lot, we'll get more people annotate the same sample so that we can get some consensus. So what do we do to kind of do this, right? So I was mentioning earlier that we get more annotators if we see a lot of disagreement. So we actually did a few more things to make sure that to resolve these disagreements. So first of all, in the initial stage of the project, we work very closely with our data vendors to make sure that the annotators actually understand our guidelines properly. And this, substantially increased in the inter-annotator agreement. We also kind of removed outlier annotations at a task level. So I mentioned earlier, so if we have 5 annotations, we just remove, the 1 or 2 outliers that are, very, very bad. And we take the mean, the simple mean of all other annotations. So what this means to say is that if you have 1 or 2 outliers, this actually doesn't affect our aggregated score. We also remove outlier tasks. So for I think a small proportion of tasks, I think about 10%, we have 3 most agreeing annotators, disagreeing a lot. And because of that, we just remove the whole thing because we believe that rather than introducing noise to our training, we rather just discard this so that we can learn from other samples instead. And by doing this, we actually improve our inter-rated agreement to about 0.79, which is a really good compared to the start where we only have like 0.465. Okay, so as I mentioned earlier, we use this dataset to train a Nemotron 4 340B RM, and this model trained on a really big base model was able to do really well. And we also trained the same RM on different open source datasets, including HelpSteer2, Open Assistant, HelpSteer, and HLHF. And we found that none of the models were able to even came close to matching this dataset. So if we see here, this is 88.8, and the next closest I think is Open Assistant at 79.1. Okay, so the next thing we then do is that we use the reward model to train aligned models. And at that time, we started with Llama 370B base, and we wanted to use our own recipe to train a model to see if we can just post-train a model to be as good as Llama 370B instruct. And we find that actually we were able to do so. So we first started with a strong SFD dataset. This is called Daring Anteater, which we also open sourced. And then we find that if we just use this method that we call STRM with 2 iterations, you can get to a really good empty bench that is stronger than both GPT-4 0613 and Llama 370B. And at this time, Llama 370B was actually the strongest model available. This was in June 2024, while I think Llama 3.1 came out in July. And this model was a model that is approximately a year old from OpenAI. So at that time, we knew that we are about a year behind close proprietary models, and about at the same level as the best open source models. Okay, so moving forward to October 2024. So this was only 4 months after that. We did a very we did kind of an ablation study with basically figuring out what's the best approach for reward modeling. And at that time we basically found that there were 2 approaches that were most popular. The first one being Bradley-Terry, and the second one being regression. And regression is where you train with Likert scores and you just predict the Likert scores of a sample. And we find that we need to have matched data for both approaches. i.e. to say you need to have the identical set of prompts and responses. They're also collected for purpose. And they have to be very high quality in order to make sure that we're not just learning on noise. And finally, we also want it to be open source data set. And so yeah, we created an open source data set to help people understand. So again, this is very top performing, efficient, and just on a 7 TB model, it actually reached 94.1 on reward bench, which was actually stronger than our 340B model. And we find that like this, the preferences released in HelpSteer2 preference was actually super complementary to ratings, ratings in HelpSteer2. And we also release some auxiliary data beyond just the preference. We also release human written preference justifications that allow them to say why exactly did you prefer one over the other. And that was, I think, a great first approach into understanding interpretable kind of reward modeling. So as we can see here, when we kind of like correlate preference to individual helpfulness, we find that basically they correlate pretty well. But there are cases where maybe you think that generally they're about the same helpfulness, but you still have a preference for one or the other. And the other thing that we can see here is that so if we just look at this plot, is that the position bias is pretty weak. So if you look at some of the earlier papers, for example the empty bench paper, you will see that it actually strongly prefers the second response. But here I think that there's only a very, very slight preference for the second response. Okay, so moving forward, we have we did some reward modeling, and we did both Bradley-Terry as well as STRM regression, which is basically Likert style regression. And we found that the optimal formulation for Bradley-Terry is scaled Bradley-Terry that scales the loss within Bradley-Terry proportionally to the preference strength. So you weigh the responses that where it says A is much preferred compared to B, and you weigh that maybe 3 times as much as something that says A is slightly preferred to B. And we found that just using when we initialize a model from STRM regression and then we further tune it on Bradley-Terry and also do a separate step on I think this is called extrapolation optimization, where we just take the delta weights and scale it up, and we found that was able to give us the best model on reward bench. Okay, so we then also used the reward model to train allied models, and specifically we use a few methods. We use DPO and variants of DPO based on our scaled method. We also use PPO as well as reinforced method. This is actually RLOO, which is actually very similar to GRPO. And we find that across all the models, so online RLHF models were actually much stronger than offline RLHF models. So if you see empty bench, that maybe PPO and DPO that are similar, but if you see all the other metrics, especially arena heart, PPO actually beats them by quite a lot. And to our surprise, RLO actually does even better than this PPO in terms of all metrics, right? So here we're able to get 8.98 as well as alpaca eval. And at that time, I think this was all state-of-the-art performance. And this really surprised us because when we wrote this paper, we actually didn't know of another lab that had experience with removing the value function within PPO. So I think GRPO only really got popular with our DeepSeek R1, but that was January of this year. Okay, so here previously I was talking about how do we formulate the best reward, but now I want to kind of take a deeper dive into how exactly do we want to formulate this data collection. And here we basically think that a richer way of collecting data can actually empower different ways of training models to do different things. And so in the first part, I'm going to talk about the inspiration. So this part actually comes from in like just reflecting about how humans learn, right? So obviously I think humans, learn over a very long period of time. We go to school, we also read books by ourselves. But at a task level, when we are doing like, particular task, typically people, do things, they give it a first shot, and then they ask other people for feedback, and then they kind of improve based on that feedback. And we find that pattern actually consistent across many different things that, me and my colleagues kind of do. Like we write academic papers, we write code, and we also kind of sometimes, make important life decisions, such as taking a job or a PhD. And we find that in each of these cases, actually, coming up with a first draft, you know, asking for feedback on it and then improving based on that first draft is super important. Like we don't just, ship the best paper or best code by just, doing it one time. But we actually do ask regular models to do that. So, this made me, think more about why exactly, we don't do that. And, I like to think in terms of analogies. So, in the first case where, we just give a model a scalar reward from reward model, it actually makes it very difficult for the model to figure out what exactly went wrong. So this is just like, if you're in school and you write an essay test, maybe you get 80 out of 100, but you have no idea where the other 20 points went. Multi-attribute reward models are kind of better. For example, in our CRI method, we propose a method to kind of give individual dimensions a reward. So this is kind of similar to, doing essay tests and knowing that maybe you got like 5 out of 5 on grammar, maybe 4 out of 5 on vocabulary, and maybe, 3 out of 5 on your essay structure. So it's a bit easier for you to learn exactly where you are not doing as well, but it's still not as precise, right? So for example, you wouldn't necessarily know where your structure had gone wrong. Was it, at the paragraph level, or was it, the entire essay? And our solution was that, we need to provide much more richer feedback. And at that time, we thought the best approach was to provide textual feedback, where, the annotator can just write anything that they think can be improved or anything that is wrong with the response, and, even potentially, suggest fixes to fix this response. And this is very similar to doing an essay test and having teachers to write comments on the sidelines as they're grading to pinpoint to you exactly, where is wrong and what you can do about it. And I think at the time when we were just working on this project, R1 was, starting to get popular, and, O1 was starting to get popular, and R1 was, came out of the blue, it took the whole world by surprise. And I was just thinking, would this new approach be kind of complementary to it, or would it be totally different? I thought that, this longer thinking approach is only very useful when the rewards are verifiable, i.e. to say whether they are correct or incorrect. And this means, at least at that time, you could only really use it for like math and comparative coding, which is different from software engineering. And for many other tasks, such as like, writing intensive tasks, you may not actually do better. So for example, when O1 Preview first released the blog, it actually showed a regression in personal writing compared to their previous generation, GB4O. So a natural question is, do you actually need, humans to give you this critique and then to improve based on that critique, right? Can you just ask an element to self-critique and self-improve? I think, there were a few approaches back then, but nothing was very general. And some evidence suggests that, non-specialist LMI, to say LMs that were not particularly trained to do something, can't really give effective feedback. And, I think also some other people were saying that it kind of works for other tasks like code, reasoning, and summarization as well. But, no one really, had any clue whether it works generally. We also have another study show that, if we just have edits, so we just kind of train a separate model to edit a model without conditioning or feedback. It's kind of useful for general domain check, but we didn't know how well it compares to edits, conditional, or feedback. But intuitively, that we thought that actually giving feedback is useful, because this gives another perspective to where exactly you want to improve. And when we trained HelpSteer3, I think this was our best model at the time. And R1 and O1 mini really set the bar on this benchmark, which is Arena Hard. And with this feedback and edit system, we actually got it to be slightly higher than the two other models. Okay, so what is HelpSteer3? So again, it's an open source enterprise friendly dataset that contains feedback, edits, and edit quality. So feedback is just a paragraph length on what is good about the response and what is not good about the response. Edits is basically given an initial prompt, initial response, as well as feedback from 3 people. How do you actually improve this response? And the last one is basically we have a pair of edits. One is a good edit that's based on the feedback, and the other is a bad edit that also changes the response, but it doesn't really follow the feedback. Okay, so now onto the distribution of the data. So prior to this HelpSteer2, we always focus on this general part of the pie. General chat domains, so no specialization. But this time around for HelpSteer3, we actually decided to get 3 separate groups of specialist annotators. So this refers to STEM, code, and multilingual kind of annotator crowds. And compared to this, where it's just basic certification, for this we make sure that these annotators are actually really specialized in their fields. So for code, we hire software engineers. And for multilingual, we make sure to hire locals with good understanding of particular languages. And we covered a good set of both programming languages as well as natural languages, with a big focus on some of the more popular programming languages like Python and JavaScript, as well as natural languages such as Chinese. What we found was that if we just use a very strong base model, this was the model that I showed in the previous set of slides, and you just include the feedback and edit system, we find that we are able to improve it across all axes. So improve Empty Bench, Alpaca Eval, and Arena Hard. And this works, even if you're dealing with a not so strong initial model. So for example, Llama 3.3 70B, and this, just always pushes it beyond what it can do initially. Okay, we also did some ablations to kind of, figure out exactly what was working and what was not. And we found that, so comparing, this was the same kind of like row as the previous slide. And we found that if you just do self-feedback and self-edit, it was indeed not as good. And for the edit training, remember earlier we had a good edit and bad edit. We found that, including some RL training with that signal was able to actually improve this process a bit better. And finally, if we don't have feedback for edit, you can see that actually Alpaca Eval actually improves even higher than this just with feedback, but Arena Hard actually dropped relative to the base model. So this suggests that incorporating feedback is useful for hard tasks, which characterizes Arena Hard, but not really for easy tasks, because Alpaca Eval is like a super easy task, super easy benchmark that was, I guess, from like 1.5 years ago. So they're very simple QA questions. We also tried scaling different parts of the system. So, this was our baseline method, which is best of n, and we use an RM to choose the best response. But in this system, we're able to scale, other aspects. So for example, how many initial responses do you want to generate? How many feedback do you want to generate per response? And also how many edits we want to represent per feedback set. And we find that, increasing each of them actually leads to quite a bit of gain. And what I think is the most interesting is that we were able to scale each of these in parallel. So basically you have maybe like, I don't know, up to 16 parallel improvement cycles. And all this can be done in parallel. So if you do, for example, 16 responses per prompt or 16 effective feedback rather than 2 effective feedback, your latency actually wouldn't increase. Whereas I think at that time, the most popular way of thinking about it was like O1 or R1. So if you want to kind of scale your inference time, that kind of like increases, I think quadratically, which is kind of bad. Okay, So the next thing that we also found was that you are able to distill these feedback edit models to kind of just do regular chat models. So earlier we mentioned that in order for this feedback edit system to kind of work, you need to let it go through the initial generation, and then you pass it to a feedback model, and then you pass it to an edit model, and you basically you're kind of like increasing the latency by 3 times. But sometimes, for example, when you just chatting with a model, right? Maybe users don't want to wait for too long. And in this scenario, we basically try to just distill the data that we managed to go through this entire feedback edit system, and we kind of produce about 20K of like prompt response pairs, and we just use that to train off the shelf model. And this model wouldn't need to like do this thinking, but it would just generate a response immediately. And what we found was that for many of these tasks, I think empty bench is like the improvement is not so much, but for many of the tasks, for example, Arena Heart, we're actually able to get super high results just by doing this distillation. And yeah, I think this kind of proves to us that for this system, it can be a good teacher for doing distillation, similar to for example, distilling DeepSeek R1 generations into smaller models. Okay, so I'm coming to the last part of my talk, and I want to discuss some promising directions for RLHF data curation. So the first part is, generative reward models. For most of my slides previously, they were all Bradley-Terry reward models, and they're super efficient in the sense that you only really require about 1 token of compute to generate the overall reward. But a trend that came out with R1 and O1 is that when you have reasoning LLMs that thinks for a bit before it generates a response, you can do very similar things with like reward models. So you can train a model to think about its rationale about how you allocate credit to each of these parts instead of giving an immediate response score. And in some of the many papers that are out there, it does show that these generative reward models were super good and much better than training a comparable kind of Bradley-Terry model. The other idea that I think would be common for RMs in time to come is that rather than just training on a generally helpful or generally harmless model, we will actually move towards kind of more criteria specific reward models. So I would just want to give an analogy, right? So here we have 3 animals: a cheetah, an elephant, and also a dolphin. So if I were to ask people, what exactly is the best animal, I think different people will disagree, right? Because maybe some people think that the best animal is the one that can run the fastest. Another person maybe thinks that it's one that is is the largest. But if we kind of change the word best to just specifically fastest or specifically largest, I think it will be much easier for reward models to learn, since it's easier and humans are able to do it more consistently. So I think we are moving towards a future where reward models aren't just about general helpfulness, but about meeting specific user demanded criteria. We also see this trend where we move from unskilled annotators. So I think the earliest, this picture is actually Amazon Mechanical Turk, where just random people going to this like Amazon provider website where maybe they earn, I don't know, just minimum wage per task, to more and more skilled kind of like annotators. So for example, here I think HelpSteer and HelpSteer kind of data set, we employ mostly college graduates. And in HelpSteer2 and later HelpSteer3, we increasingly hire specialists, for example, software engineers with a few years of work experience, so that because only this experience guarantees that they're able to understand what they're doing rather than just giving random annotations and random comments. A good case study for this is, I think 2 benchmarks. So one of them is called Health Bench, the other is called Paper Bench. Both are from OpenAI. And what they do is that rather than, they kind of combine these ideas where you have a generative reward model, and in which case I think that you're just using off-the-shelf models like O3. And they are also, getting criteria specific, like ratings where you just see whether it meets a particular criteria. And finally, it's also by total experts, right? So for example, Health Bench is just totally annotated by medical doctors, whereas Paper Bench, the kind of the criteria are being annotated by I think authors of ICML papers. So increasingly we see in these benchmarks from these proprietary providers that they are kind of combining all three trends together. So I guess just to end off, I think for a lot of this task, these are super hard, super frontier. But I think one thing that kind of like is very familiar to many researchers here is kind of like just submitting a paper to a conference and having other people rate your paper. And I think it's important as we come to this level of specialization to just think in the future we maybe want our papers to be reviewed by LLMs. Should we trust them for allocating rewards for which paper gets into a conference, which paper gets maybe a best paper award, or should there maybe be some kind of like efforts for determining whether we should just maybe say, okay, this has to be done by humans. Yeah, so that's the end of my talk. Thank you.